Welcome. We have a quite tight agenda today, so we'll go fast. Me and Alex will share the first half an hour, and then everybody else from the presenters gets half an hour for the talk. So welcome. So what we did for the cybersecurity, it's actually the part where I put most of my time. Maybe a bit with Jonathan and Wilhelm as well. But in this part, what we did was that we built this tool that I actually showed on the demo with Albert. So part of that code that I actually tested was the tool that we've built during this sprint. And what we focused on mostly was finding out both testing different models. So we created this new model that we called cybersecurity, bidirectional, so on. And then we tested this pipeline on different data sets for security analysis. We did the benchmark with existing data sets, with existing tools. And we also look at new vulnerabilities from that. What we have also tested is the cross-language thing. So we've long time wanted to understand if these language models are really so language dependent, so to say. So we had one data set in our tool that we had from Java, and we as a reference data set, and then we had our examples in C#. No, sorry, C++. And it turns out that actually, and then we tested it Java to Java versus C++, and then we translated all the examples from Java to C++. I rewrote them manually to C++-like, and then looked at how that would look like. And the answer was that actually Java was much better than C++ in terms of accuracy and performance. But what we also did is that we actually look at different models. This Cyberta model is a small model, only 12 million parameters, but we trained it on the code that was similar to the model below, which we used last spring in the fall. But we trained it on Wolf SSL, which is an SSL protocol that is used in a lot of embedded systems, but it's also known to have quite many security vulnerabilities. So it's not as good as the OpenSSL, but it's very specific and it's used. And the reason why it's there in the first place is because this code has been tested on a lot of small devices. So the code was actually tested and works on a lot of small devices and processors, which OpenSSL doesn't, right? So sometimes when you do development of embedded systems, you're just stuck with that anyway. But in order to do whatever we wanted to do in our study, we actually packaged this into a tool. And what we did in this sprint, we focused on looking at the quality of this being able to recognize vulnerabilities. So we looked at finding more examples. In previous sprint, we created examples ourselves, me together with some colleagues from Grundfos. But in this sprint, we actually look at those data sets that contained examples from of vulnerabilities, and we tried to see if we could look at them. Now, the interesting part, which I thought was very good for these tools, was that for every staple, for example, the second one, improper input validation was the vulnerability we focused on mostly. It contained nine examples, but also 9 counter examples of this. So basically the same code, but without the security vulnerability in that. I thought it was great, but as you would see here, basically it doesn't really matter. So what happened in that data set, for example, is that when we put our reference code, mix it with those examples, the examples of vulnerable and non-vulnerable code are always the closest one to one another, whereas the other examples are spread all over the place. So that basically means that the data set wasn't really very good for that. And if we look at precision and recall, they were actually quite bad. For the binary classification, we only got about 67%. For different reasons. I mean, one reason was that the code that we used for testing was the code that we used from previous studies, which was from embedded software development, and it was actually part of the code that handled HTTP requests. But if we look at the code that we used for validation over here, it is much broader. For example, this SCE8, it has user bank account validation, right? So it was actually recognized correctly, but I wouldn't really trust it because it could just be completely by chance, so to say, right? I mean, the code that we tested over here and our code that was that we used for reference was completely different. And if we look, for example, this flag no validation, it was part of the code that was actually used, that I thought that was the most similar to the code that we had in our database. So this should actually be correct. So yes, the precision and recall are a bit higher than chance, not so much, but I wouldn't trust these predictions so much. And what we did also is we actually, or as I said, I took all these Java examples and rewrote them in C++ to C++. Not always really trivial and not always really fully correct, because some of the Java libraries imports basically don't exist in C++. So I didn't go as far as actually rewriting this completely, but I rewrote it kind of that it would compile, but not really fully tested the same way. And of course, the precision was a bit lower, but recall was a bit higher. So we were a bit better in finding vulnerable code. So we missed on the 2 examples, but we also were able to find more false positive examples, which is not really great. I mean, it's great it's good in a way that we miss few vulnerabilities, but it's not very good because there is a lot of extra work for the designers in terms of looking for vulnerabilities that are just not there, which of course reduces the trust in the tool and reduces the work that we were doing. Yes, and then we are also working on comparing to other tools. We actually tried to do that. We found a lot of tools that you can just connect to your GitHub repository and then just apparently validate your code. But as it's all, well, not always, but quite often, these tools just don't work on that particular repository, or don't require the code to compile, or some libraries are missing and things like that. And apparently, many of those tools focus on specific vulnerabilities, and most of those vulnerabilities have to do with web systems. So, for example, SQL input validation, buffer overflows, those kind of things, which we don't really have and are not really interested in. So, what we also did on that was, for example, once I got these not so encouraging results, I started reading the examples that we got from those databases. And then all of these databases and links that I showed you, they are published papers, they are established research groups, established companies that provide you examples. Now, then the example looks like this. I mean, it's not even complete, this example. This code doesn't even compile. And it's an example of no validation source code somewhere. To be honest, I don't know where this no validation doesn't happen. It's hard to say for me. I look at the code that was provided as a counterexample. It looked very different. Didn't even have the same parameters, so to say. And as you see, this code is not even completed. It has some sort of token in the end from I don't know where, which basically started making me a bit nervous about how we validate security of our software component in practice, because this, as I said, comes from an established database. So in the next sprint, what we do is we filter out those examples, we create new examples, we find examples that are validated and actually we can believe, and we translate them from, for instance, Python to C++ to increase the database. And in the fall, what we will do is I will visit Grundfos again to analyze their code. Plus, I will visit Axis to do the same thing with their code and see where we are in terms of real security vulnerabilities. Yeah, and I think that's it. And I'm just about on time to leave over to Alex if or unless you have any questions.